Welcome back to another episode of Disc Golf Physics. I brought with me a guest star, my colleague and friend, Bradley Treece. Dr. Bradley Treece is a new member of the Mercyhurst Physics Department. And we have in the background, in the peanut gallery, Professor Paul Ashcraft. So you have the entire Mercyhurst University Physics Department at your disposal to talk about disc golf physics. So we have talked about, together, you and I, moment of inertia, why discs are shaped the way they are and how that affects how they spin. We also talked a little bit about why discs skip because of their angular momentum. And Brad's going to go into some of the details of the math, the numbers, and how those things work together, and the vectors.
Yes.
So I'm going to get out of your way.
Awesome. Yeah, so Joe, you've talked about how if the disc is spinning, it has angular momentum, which is related to the rate at which it's spinning, as well as its moment of inertia, which you've talked about. And so when we start talking about forces and torques and how things are going to move when different things affect the motion, you kind of have to talk about the direction and what's going to cause what to move which way. So we kind of do need this concept of vectors, which introduce the concept of direction. And so I think a good place to start is to understand when we're talking about angular momentum or angular speed, what the direction of those quantities are. For a lot of this, I think we're going to deal with discs, when you look at them from above, are spinning in a clockwise direction. And in physics, we use what's known as a right-handed coordinate system rather than a left-handed one, because evidently we like right-handed people more than we like left-handed people. But what that means for our vectors is that when we ascribe a direction to a spinning object, the direction that we ascribe is one which is right-handed. So if you imagine your fingers as curling around in the direction that the disc is rotating, clockwise from above, the vector that we associate with that spinning motion is downward. You can think of it as, here we have a spinning top. The top spins in this direction, and the axis about which it spins is vertical. And we use the right-handed sense to describe that vector.
And a clockwise motion from above is the same as a right-hand backhand throw.
Right, yeah, so if you're throwing right-hand backhand, the disc will spin in a clockwise fashion if you're looking from a drone above. If we look at a slight angle and looking from above, it's going to spin in the clockwise direction. The angular momentum that we use to describe that will point down. And the same applies for the angular velocity. And since the two are just proportional to each other, this being the moment of inertia, which multiplies the angular speed or the angular velocity to give us angular momentum. Now the question becomes, whenever something acts upon a spinning object, how is the motion affected by that spinning? So I think if we spin this, I have it set so that it should spin in a clockwise fashion. As the gyroscope begins to tilt, it will do what's known as gyroscopic precession. And you can already start to see that is starting to take effect, where the axis of the spinning object is moving around in a circle. And so as it gets slower and slower, the effect of gravity, which is making this happen, becomes more significant until it completely slows and comes to a stop. How do we understand what's going on here? The gyroscope is spinning. It has angular momentum in the exact same way that we described with the disc. And gravity is pulling downward on the gyroscope. So if I draw this in a little bit more of a top shape, so here is the spinning portion of the top. Here is the axis through which it spins. And because we set this up to spin in the same way, the angular momentum still points downward along the axis of the top. Now, what does gravity do? Gravity pulls straight down, and it pulls from about the center of the top. So this would be the force due to gravity. Now we know what happens if an object's not spinning. If an object is up in the air and you allow gravity to act on it, it falls straight down. When you introduce angular momentum, something a little bit different occurs. So the top, which is perched upon its stand, is allowed to rotate back and forth. And so gravity acts to pull it down along this pivot point. So it's sort of constrained by the fact that the bottom of the top is fixed and gravity will pull down on that. And we call that kind of force, where the force is not acting about the location of the motion, the center of the motion, to be a torque. And so once again, our right hand comes into play when we try and describe, well, what direction is the torque? So torque comes from what's known as a cross product. We don't need to go deep into the math to understand the cross product and what it implies, mathematically speaking. We just care about the direction of this torque. So R is the vector which points from the point of rotation out to where the force is acting from. So the force pulls on the center of the top and it pivots about this point. So R is the vector from the pivot point out to where the force acts. So when you're trying to find the direction of the torque, you again use your right hand, and there's a couple different ways in which this is formulated. The one that I often use is that you put your hand at the location of the pivot point, so where the top is about to pivot. You point your fingers in the direction of that R vector, that displacement vector we talked about, and then you allow your fingers, not your thumb, but your other digits, to bend in the direction of the force that's being applied. Finally, your thumb takes the role of the torque and indicates that it's into the page, or into the board in this case. So now we've got all kinds of vectors flying around on the board. So let's just draw the torque and the angular momentum for a second. So you have the torque, which this symbol just means a vector that points into the page, and the angular momentum. And so these two vectors are related to one another. So what, for example, if I apply a torque to this disc, let's see here. So if this is the center of the disc, here's where I apply my downward force, it causes the object to rotate. So torques affect the angular momentum of an object. So in the same way, the torque is going to have an effect on the angular momentum. And in fact, much like forces affect velocities, torques affect angular momentum. So this torque is going to change the direction of the angular momentum. And so if it's a vector that points in this direction, the angular momentum, and you apply a torque in this direction, the angular momentum will change its direction. And so this is exactly why the top axis precesses under the effect of gravity. Okay, so this is a little bit of review of some of these concepts and introduction of the vector nature so that we can get back to the important stuff, the disks.
All right, so from what I gathered from what you were just saying, that as a force acts on a spinning object, the torque that it feels actually works perpendicular to that direction of that force, which is why it was kind of spinning around,
right,
even though the force was down.
Exactly. The motion that it tends to move is actually perpendicular to the direction that the force is pulling on it.
All right, so when a disc flies through the air, it has a really unique pattern that we try to shape. as we're throwing discs in the woods.
Mhm.
So how does this idea of this precessing gyroscope translate into how a disc is going to fly?
Right, yeah. So you have a spinning disc, which also has angular momentum. And because the forces that act upon it are going to move it in a direction perpendicular to the direction that the forces actually act, then you're going to get these weird paths that are actually perpendicular to the direction of the forces that we know, which are lift and drag on the frisbee. And so those act kind of in this direction, whereas the motion of the frisbee is kind of perpendicular to that.
All right, so we can kind of model or explain this flight path similar to how we were trying to explain the gyroscope, but in terms of these other forces that are acting on the disc.
Right, yeah, so the more natural forces on the disc apply lift and drag versus just the gravitational force. The gravitational force on the disc is not going to play as much of a role in the tilted motion of the disc.
All right, let's see what you got.
All right, so I think it's good to start a little bit of a review of where those forces come from and sort of why they act in the direction that they do, lift and drag. So I've drawn two different scenarios here, one where the disc is on the upward part of its trajectory and one on the downward part. And in both cases, we're still going to be dealing with a disc which is spinning clockwise from above, so we have this mostly downward angular momentum that acts or the direction of it is perpendicular to the disc motion, or the disc spinning itself. So where does lift and drag come from? Well, a better fluid dynamist than I would get into Bernoulli's principle and many complicated things, the details of which are way beyond what we even care about here.
Sure.
But the nice thing about physics is that you can just look at the net result and describe what's happening in terms of what we call net forces rather than understanding the details of where those forces came from.
For the curious viewers at home, Bernoulli's principle talks about how when we have airflow over top of the dome of a disc or an airplane wing or something, there's a pressure differential between the air up here going over top and the air down here going on the bottom. It has to do with turbulence and differences in pressure with velocities of fluids. And it's a little bit complicated, more than we really need to get into.
No slip conditions, lots of things that really just like would complicate this problem way more than we need to. So
Sure.
we can just look at the largest effects, which are we have a disc flying and there's air exerting a force on the disc, and Newton's third law says that the disc also exerts forces on the air. So what effect does that have? Well, we can assume that the air is mostly coming in parallel to the ground. If it's not, we can reorient ourselves such that this is basically the case. Just look from a different angle. So for this discussion, we'll just say that initially the air comes in with some horizontal velocity, and after interacting with the disc, what we find is that the air that was in contact with the disc has slowed down and it's changed direction slightly. So it's at somewhat of an angle downward, and the slope, it's not moving as fast anymore.
Relative to the disc.
Relative to the disc and to the ground, whichever frame you're choosing to work in. So if we put these two vectors next to each other, so the airspeed before and the airspeed after, the important facts are that the final speed, which is indicated by the length of the vector, is smaller than the initial speed, and that it's been deflected downward. So we can talk about the change, which would just be the vector going from one of those, from the initial velocity to the final velocity. So that's the change in the airspeed or air velocity. So why is this important? Well, speed or velocity and momentum are related just basically by the mass of the air, and so you can equivalently think about the velocity vectors that I've drawn as momentum vectors. And a change in momentum is induced by
a force. We talked about impulse in a previous video, and impulse is change in momentum, and impulse is related to force that occurs over a certain length of time.
Right. So if we think of this as the direction of impulse or the direction of force exerted on the air by the disk itself, then we know by Newton's third law that the force exerted on the disk is in the exact opposite direction.
Equal in magnitude, opposite in direction.
Right, so these vectors are the same length and they point in exactly opposite directions. So the force on this disk is kind of up and to the left, which is what you may expect, because if you look at the different components of the force, we can break this into different pieces. There's a drag force, which acts backward on the disk, so we can call that drag, and a lift force, acting upward on the disk.
Now, disc golfers will know the flight number system. The second number is called the glide of a disc, and that's associated with the lift that the disc is going to experience. So the amount of that lift force is going to be determined by a bunch of different factors, the nose angle, but also the disc itself has some impact on that.
Yeah, so this analysis works equally as well for the disc when it's on its downward part of its motion. And what you're going to find is that the direction that the airflow is deflected just changes. And so what you find instead is that the lift acts downward and that the drag still acts backwards to slow the disc. So if this is the center of the disc, lift is no longer lifting but causing the disc to fall, and drag is still slowing the disc down. So those are the forces acting upon the disc. And so I'm going to clean this up a little bit so we can see how those forces affect the angle of the disc as it moves.
Yeah, this is going to be cool. All right, so we have all these forces acting on the disc. We've got lift, we've got drag, those are going to be major forces. But we said like gravity is acting down and it affects the disc not in the direction of the gravity.
Right.
So how do these forces kind of come together as the disc is flying through the air?
Right. So while it's useful to discuss lift and drag separately in some contexts because you want to see how much the disc is going to rise or how much is going to be slowed down, for this discussion, it's a little bit easier to lump them all together and see how they act in a total. And so we call that the net force, where you just take and add the two forces together. And so the overall force for the upward moving disc is backwards and upward, whereas for the downward moving disc, the net force is down and also backward. And so those forces together, the net force, are going to act on the disc to affect its angular momentum and cause it to tilt to the left or to the right. Because again, even though the force is in this direction, the motion that induces is going to be perpendicular to the force itself. So sticking with this case to start, we need to figure out how this net force is going to induce a torque which affects the angular momentum. So in the case of the spinning top, you had the stationary point of the top being at its bottom, and then the force acts from the middle to try and generate a torque in this direction. So in the same way, we need to see where the disc is going to pivot about, which it will be its center of mass, which I've handily labeled in pink here, so it will tilt one way or the other about its center because a force acts somewhere that is not the disc's center. So we need to think about where on here the forces are going to act, and it turns out that they're not going to act exactly on the center. The reason for that gets into more complicated fluid dynamics, so the net action of the forces occurs where we call the center of pressure. So the center of mass kind of describes the average of where all the mass of the disk is, and the center of pressure describes the center of where the pressure acts. So each point on the disk has a different air pressure because the speed of the air varies over the surface of the disk. And so what you find is that the center of pressure is actually a little bit behind the disk. So I'll mark it with, or behind the center of mass. So I'll mark it there. So now we have the location of where the forces are actually acting to cause the disk to rotate, and it's going to be at the location of the center of pressure. And if the force is roughly in this direction, variability in speed and angle of attack and things are going to change the angle that this net force acts upon the disk, but more or less up and to the left. And so, much like before, we want to know the vector from the center of rotation, the center of mass, out to where the forces are acting, which is given by this vector. Once again, we use the right-hand rule, your hand at the point of rotation, and then fingers in the direction of the displacement vector, we call it, and they curl in the direction of the force so that your thumb points into the board. So we find that the torque acting upon the disk, which I'll draw right here, acts in that direction. And calling back to what we discussed before, the torque acts to alter the angular momentum. So if the torque is acting into the board and the angular momentum points down, then the disk tilts.
And it's going to tilt like this,
like that.
which gives us our right hand turn. We actually, the word is turn on the disc, and at the end it's supposed to come back and it fades. The terminology from disc golf is that it would fade back to the left.
Right. And so the way that happens is that now the net force is, instead of pointing upward, points downward on the downward attack of the disc. And so following the same procedure, you draw the displacement vector to where the force is acting, you draw the force itself, and when you take the cross product, R cross F now has your thumb pointing to the board.
So the torque is coming towards the camera right now.
So this symbol we use for out of the board, indicating that your angular momentum would like to rotate this way, and your
So it's
disc
going to turn back to the
turns back to the left on the end of the throw. We hit all the points?
I think so.
Okay, good.
Comments?
I'm good.
So you've actually been out disking with me. Brad's only dabbled a little bit, but Paul, you've actually been disking with me before.
Yeah,
So
yes.
so you've seen some of these turn, fade, and action.
Yes,
It's kind of neat.
it is kind of neat. Almost like bowling.
Yeah, there's a lot of science that goes into bowling as well.
Instead of lift and drag, you have friction, but you
Yeah.
still have a spinning bowling ball that has
Yeah.
angular momentum.
Exactly.
Yeah.
I'm trying to get the curve a certain way.
So when the oil is thicker and the ball has less friction, it tends to follow a more straight line path until it hits the dry boards, and then it pulls at the end of the throw.
Right. And in bowling, I'm strictly a straight ball person. And when I was golfing, I just tried to be as straight as I could be. Because I don't know the curves.
Yeah, that's actually one of the harder shots to throw is a straight shot in disc golf, and because of all these forces acting on the disc. So, thank you guys for joining me.
Sure.
Hopefully you can
Thanks,
join
Joe.
me for some additional episodes.
Yeah.
Thank you guys for watching, and please leave a comment. Let me know what questions you have, and I'll pass them on to these guys, and we'll try to get to them. So, excellent. Thanks.